All right, let's get started. I'll be talking about extracting principles from biology for application to robots, running robots using optimization. So we'll start with the context, how it fits into the biomimetic design process. Talk about how we extract principles. It's a general method, and examine it using a case study. I'll talk about future work using the method, conclusions and contributions of the method, and open questions about the method. So the biomimetic design process, as our lab sees it, begins like the typical engineering design process with a problem statement, continue on to generate ideas, such as brainstorming exercises. You select ideas based on certain criteria, go on to conceptual design, detailed design, etc., maybe iterate. But what sets it apart is that you take principles from biology. You don't just copy the biological solution. You take ideas and you apply them to the idea generation and conceptual design phases. And so my goal is to distill or extract from biological examples principles that we can use, or nuggets of intuition, specifically as they apply to robots, not necessarily how they apply to biological systems. But how do we do this? So I'll illustrate with an example. Begin by observing from biology. It was talked about this morning. Swing leg retraction is when the extended airborne front leg rotates rearward before the foot touches the ground. And so there have been several hypothesized benefits for this, such as that it reduces touchdown loss and improves overall energetic efficiency, and that's what I'll focus on. Model the situation. I'm interested initially in the Fides robot, but we'll generalize to other machines. The joints and legs of distributed mass, we model them with the distributed mass. Swing leg retraction rate is measured as the angular velocity of the virtual leg, which extends between the hip and the foot. There are torque actuators at all the joints. The robot lands with a bent knee at a specific angle so that this linear spring can engage during stance, and then the torso is fixed like the real robot. So that's the model, and now I'm going to optimize for minimum mechanical cost of transport using general pseudospectral optimal control software. For a limit cycle running that minimizes that cost of transport and constrains the swing leg retraction rate. So I start with an initial seed, a random seed. It's a random collection of states at random times. And GPOPS returns limit cycle motion. So this is an example at 2 radians per second retraction rate. This is what I get out of it. So I begin with lots of different random seeds for each swing leg retraction rate. And I end up with different limit cycles, local optima. But I get a trend. As the swing leg retraction rate increases, each of these is a local minimum, and they cluster towards an apparent boundary. And so I interpret this as the global sensitivity of the mechanical cost of transport as a function of swing leg retraction rate. Now, notice that the effect, each of these local minima also has impact losses. The trend is different. It goes in the opposite direction. So we can conclude from this that for Fides at least, at this speed, swing leg retraction can improve the energetic efficiency up to a certain point, as measured by mechanical cost of transport anyway. But the effect is relatively small. If you look here, the ordinate is only a few % change, and the effect isn't actually due to touchdown loss reduction, which you might have hypothesized, I at least thought initially. So by varying other parameters, or as Dave Grimmy suggested, allowing the optimizer to choose them, conclusions can be generalized to a broader class of machines rather than a particular robot. And so that's what I'm interested in, is taking intuition about robots in general. So future work using this framework, I want to study topics like leg morphology and how that affects biped running speed and efficiency, gait transitions, also as David was interested in, spine flexibility on running efficiency and speed, and tails on maneuverability. And we can use other cost functions and study other effects. Conclusions, this is a framework for studying inherent properties of dynamic systems and distilling ideas from our observations to be used as intuition for design and suggestions for more detailed study of particular systems. So the open questions that I have, to what extent can we trust these lower dimensional models of running and walking for building or intuition? This is a relatively high dimension. It's not the SLIP model, but it's not a fully realistic robot either. Is a cluster of the local minima, like I get, good enough? Does that represent a global minimum? Or is it good enough for our purposes of studying the effect of one thing on another? And we ask the question, what is the effect of this swing leg retraction rate on that energetic efficiency, but we get an answer of the form with this process, the effect of swing leg retraction rate on the optimal or minimal value of the mechanical cost of transport. Is that really what we're looking for? So thank you for listening. I'll hopefully take some questions.
Why do you have a knee? Why do you have a linear spring?
This is not my robot. I'm working in collaboration with Daniel Carson at Delft. And so it helps save energy during stance so that the motors don't have to produce that. The choice of linear spring, I don't know. That'll be, actually, I think he's going to be here at the conference to discuss that. Yes?
I'd like to suggest it's more useful to think in terms of ground speed matching than swing leg retraction. In other words, worry about the foot in world coordinates, not in robot coordinates.
We have. In previous studies, we did look at that, and it's actually not the ground speed matching in terms of the x velocity that it should match. At least for telescoping legs, we found that the speed, the component of the speed in the direction tangential or perpendicular to the axis of the leg, that was the most important thing. And when that was 0, we ended up with 0 touchdown. This is not true when you're talking about a knee leg, especially one that lands with a bent knee. So that's why I didn't do that in this case. I'd love to talk about that more. We found some interesting things. Yes? What do I mean by optimal? Of course, optimality is always defined by a cost function, and because we only have local minimizers, and I use, I mean, there are some situations when you can get global optima, but I'm getting local optima, so in the nearby neighborhood of these limit cycle running solutions, there's nothing that you can do that will improve the mechanical cost of transport. Yeah.
You believe what you just said?
So are you questioning whether the algorithm is working correctly?
Yes.
Yeah, I don't have a reason to suspect that the algorithm is not solving the problem that it is intending to. So I know that it's not always, it's difficult sometimes to verify that the action is positive definite and you're, et cetera, but I believe in, I would doubt my setting up the problem more than I would the general.
Well, do you ever get the same dot twice?
I don't, and that's what I explained, no, not necessarily. From the same seed, yes. Sorry?
Two different seeds, you get the same input.
I'm sorry, let me repeat the question. I forgot to be doing that. The question was whether I get the same point twice from two different seeds. And no, not necessarily. I think that as I set up the problem, it is plagued by local minima. And so yes, in the neighborhood just surrounding that seed, or that solution, it can do better. I'd love to okay. Yes?
With respect to the first point, would you trust the models if you would make the robot behave through feedback control like the low-dimensional models?
The question was, do I believe that the model would would allow me to predict a feedback controller that would work on an actual robot?
Well, you say should we trust these low-dimensional static models, and why should we trust them?
Mm-hmm.
And if you make the robot behave through feedback like one of these low-dimensional models, would you trust it?
We're finding that out. I'm not certain, and so we're trying to find that out. The question is whether we trust these results in simulation, considering it's a lower dimensional model. There's a paper that Daniel and I are working on, and we're actually applying these sorts of things with the actual hardware. We've got hardware to test it on. That's why I'm doing this for particular hardware, and so we'll try to verify whether this is accurate in this particular case. Yeah. Yes?
So why didn't the optimization find a solution that touches down with 0 collision velocity?
Because, okay, the question was why didn't the optimizer find something that touches down with 0 collision velocity? Because well, first of all, we can't have 0 collision velocity because of the way the robot works. It has to land with the leg at a certain angle in order for that spring to engage. And so we can't have leg extension. So it can't absolutely 0. It could match the tangential velocity if it wanted to. But it turns out that impact loss is not the whole story. We're considering all of the mechanical work done in the cost of transport. And the work lost at collision is a small part of that.
Then the question is, is the loss? So.
Yeah, the loss was on the order of 4 to...
No. So what are you...
What are these other losses? Just the work done to swing the legs is some of it. It requires energy to accelerate the legs back and forth. Also, pushing off, adding energy, in addition to the spring, that there's probably some work done to slow the robot down and push off again.